this computer. Right, good evening again for the benefit of the recording. Good evening to Justin Tabbett, who is going to be our speaker tonight. He's speaking about the effects of cosmic rays on our atmosphere, which, while I'm sure a lot of us here have got muon detectors and record the effects and the scattered particles from cosmic rays at ground level, we're only seeing the ones that make it to ground level. So Justin's work, as I understand it, has been looking at what happens to those that don't make it to the ground and do things and produce radioactive products in the atmosphere. So I'm going to ask Justin to take the floor. You should be able to share your screen straight away, Justin, and we'll proceed without any more ado.
Okay, thank you very much. Can you see that?
Yes, we can.
Perfect. Yeah, so thank you for having me. And my talk is going to be on the development and deployment of a radioactivity detector for atmospheric measurements. Um, and so, in terms to start off with context page, I'm going to tell you a little bit about my background, and then that I've broken up the talk into a few different sections. So, cosmic rays and ionization, the detector which I was working on for my PhD, and then I'm going to look at some instrumentation development, and then conclude with the high altitude balloon flight. So I completed my undergraduate integrated masters in physics with industrial experience at the University of Bristol, um, during which I completed my placement year as a science communicator at the ISIS neutron and muon source and the Central Laser Facility in Oxfordshire. And that essentially was a position split between ISIS and the CLF. And I was writing science highlights, interviewing scientists and engineers, and essentially engaged with a variety of different stakeholders. Um, the article you can see on the bottom right there was a sort of feature that I'd written about neutrons and muons and some of the research that ISIS had been doing at that point. Um, and then after my undergraduate degree, I did a science journalism internship at the European Southern Observatory. Um, and that was very similar, except in an astrophysical context. There was a lot more evaluating research and research articles for scientific and public interest, but it amounted to writing press releases, blog posts, and those kind of things. And on the bottom right there, you can see one of the blog posts which I'd written about a lab scaled, extremely large telescope. And then after that, I started my PhD in aerospace at Bristol, my viva, which I had on Wednesday. So, part one, cosmic rays and ionization. Cosmic rays are essentially high energy particles from space. They're mostly highly energetic protons, but can also include helium nuclei or alpha particles, and also some heavier nuclei. As to the exact origins of cosmic rays, um, it's it's not an open and shut case, but it's thought that they can that these particles can become highly energetic through interactions around black holes and supernovae. And this image you can see on the right here, that's SN1006, and that was captured by ESO's Very Large Telescope. Um, and the reason why I'm showing you this is because it's thought that interactions in this image could be a cause of a possible origin of cosmic rays. So you have very fast moving protons in the gas shock region of this supernova remnant. And when these protons interact with the shock front, that could cause them to become more energetic and accelerate. And then these highly energetic protons could fly off into space until they arrive at Earth. So, thinking about Earth's atmosphere, there are a few different layers. Um, and furthest from the Earth's surface, you have the exosphere, and then closest, you have the troposphere. And then just to give a little bit of context as to what's in these different layers, you have the International Space Station orbiting at approximately 400 kilometers. You've got high altitude balloons at about 30 kilometers, and then most of your commercial airline flights, your international flights, are going to be at about 10 kilometers. Um, and as cosmic rays and energetic particles from the sun interact with the Earth's atmosphere, it leads to the creation of charged particles. And so you can obtain a charged particle concentration altitude map like this. And what this is essentially showing is that in the exosphere and the thermosphere, you get a large number of charged particles, and that's primarily at that height caused by the absorption of solar extreme ultraviolet particles. Um, and then and then the charged particle concentration decreases until you reach the mesosphere and the stratosphere when you start to get an additional increase in these concentrations. Excuse me. Um, and it's really this cosmic ray layer that I've been interested in working on. So, what how do these charged particles get created in the atmosphere? Well, one mechanism is air showers. And so you can have a primary cosmic ray, a highly energetic proton, for example. And once that hits a sufficiently dense area of the atmosphere, it can induce an air shower or air showers, which are essentially cascades of particles. And so what can happen is it can generate pions, muons, neutrons, gamma photons, as well as electrons and positrons. And these charged particles can contribute to the ionization of the atmosphere. And it's also then possible to measure this ionization owing to cosmic ray interactions. The five plots you can see on the left are all count rate altitude plots taken with measured by balloon flights carrying a Geiger sensor, which is a type of Geiger counter that's interfaced with a radio sonde. And I'll touch on that a bit towards the end. But essentially, you have this very characteristic shape, which is the same charge, same as you can see there with the uh, peak in the cosmic ray layer. Um, but one thing that's really not captured here is the energy of the part of the ionizing particles which are being detected. And then the final plot on the right is a a temperature altitude map, essentially showing that these instruments are exposed to very cold temperatures for the duration of their flight. Uh, and so now I'm going to talk to you about the microscintillator radioactivity detector. So it's an ionizing radiation detector, and it's got a sensor composed of a cesium iodide thallium doped scintillator coupled to a pin photodiode. The detector itself is quite small. It's about 5 by 11 centimeters, very lightweight and very low power. And it's capable of measuring both energy and count rate, whereas Geigers, for example, are only going to tell you about the count rate. And you can see this is just an illustration of the board and the location of the sensor there. So in terms of the detection principle for this detector, it starts off with ionizing radiation interacting with the scintillator crystal. And what will happen is this ionizing radiation is absorbed by the crystal and it will then emit light as a result. This light pulse is then detected by the photodiode, which in turn turns it into a current pulse. The current pulse then passes through some electronics, resulting in the creation of a voltage pulse, which then passes to um, some signal conditioning circuitry, um, eventually reaching the measurement stage, of which there are three main parts. There's a Schmidt trigger, which essentially just controls the measurement in the microcontroller, tells it when to start. And then there is a valley detector, which is a negative peak detector. And then there is the pulse height, which is determined by the difference between the reference level obtained from the analog pulse and the minimum from the valley detector. And the idea here is that the size of this voltage pulse is proportional to the incident radiation. And then again, each event is time-stamped. But what I really want you to remember is that here, the pulse height is equal to the reference minus the valley, or Vn minus Vp. Um, as an example of some data, this is the output that you would get. Apart from the final column, that's something that I've just added on to illustrate. But essentially, it's saying that the 63rd event is detected at 120.79 seconds with a pulse size of 86 ADC or 420 millivolts or 1063 keV. um, and so, uh, what you can do once you have a sufficient number of events, you can bin those events to create a pulse height spectrum, and you can perform an energy calibration to determine the relationship between the pulse height and the energy. What you can see here is just a GIF of, I think each one I programmed it to show 2,000 more events. But you can see as you leave the detector running for longer, it starts to populate more bins, and you get this you get this energy spectrum. And this is very typical for a terrestrial background spectrum, where you have a greater abundance of low energy ionizing events and fewer counts as the energy increases. This is indicative of the environment, but also of the detector's response, where it's more sensitive to lower energy particles. But as you can see towards the top end, you still do get a few you still do get a few events being measured. Sorry. As I mentioned, you can also group the counts by time to obtain a count rate. And this is fairly typical behavior from a background count rate, where at least in Bristol, you end in the labs that I've tested in, ends up being about 8 to 10 counts per minute. And this is just hourly count rate scaled to to show you what the equivalent rate is at counts per minute. In terms of some interesting deployment cases, so uh, one detector was deployed on the SAIL campaign, which is a space atmosphere ocean interactions in the marine boundary layer campaign, and it was the detector was operating alongside some other instrumentation. Part of it was part of the data available. The detector was on a journey from the Azores, which is some islands off the coast of Portugal, some Portuguese islands, and then it followed this trajectory. But I'm not going to show you data from that campaign today. Um, I'm going to show you here instead a commercial passenger flight. So this data was obtained thanks to a colleague, Ralph Lawrence, who had taken one of the detectors in his hand luggage and essentially had operated the detector at cruising altitude of 11.3 kilometers on a flight from Japan to the United States. I want to point out just how different this spectrum is compared to the terrestrial sort of surface level data set. Um, because you no longer see that same decrease or low number of counts at the higher energies. And that's because you're in that troposphere, almost starting to enter the lower stratosphere, where you get more interactions from cosmic rays. Um, and that's why you get so many more ionizing events detected at these higher energies. And also to mirror that, the count rate is much higher, about 20 times higher than surface rates. So in this particular data set, the average count rate was 180 plus minus 30 counts per minute. But as I was saying, it's really the beginning of that cosmic ray layer. So what you may want to do instead is put it on a weather balloon, a high altitude weather balloon. But there are a few different considerations before you do that. One of them is data retrieval, because when you put something on a balloon, you're not guaranteed to get it back, so you don't want to be storing your data locally. Um, so I'll talk more about this later as well, but this is a Pandora, which is an instrument interface board. And essentially, what it does is it manages data from add-on instruments and passes them to a radio sonde. The radio sonde can then transmit the data down to a ground station, and that mitigates this issue of potentially not getting your device back. And then another aspect which I've mentioned was temperature. So there was a prototype flight with one of these detectors. And this was the temperature profile. So you can see that it reached about negative 60 Celsius, and then was between minus 40 and minus 60 for the duration of the flight. And so you need to make sure that your equipment can operate under those conditions. And that's a picture of the early prototype version. Um, the actual sensor is in the silver box, and then this is a radio sonde stacked on top of it. Okay, so instrumentation development, the low temperature performance. Uh, with the detector that I was working on, you would observe a shift in the pulse height spectrum when it's cold. And this makes it seem that the detector is much more sensitive to these higher energies when it's cold, which is a little bit concerning because you would want the response to be consistent. Otherwise, you end up having to do lots of corrections to your data after the fact. But just to illustrate what's going on here, in the initial 24 minutes of this data set, when the detector was still warm, you end up with a spectrum that looks very similar to what I've shown you already. But then towards the end, you can see that essentially all of the counts are now located in a few different in a one large peak in one area of the spectrum. And so it's a bit concerning as to why that's happening. So initially, I thought it was due to the microcontroller on the board. Um, and so I set up this experiment where I had the detector outputting its analog voltages to a breadboard that contained the exact same microcontroller running the same code, and both of those would output the data to a computer. Um, excuse me. And then what you could do is you could cool each of these components individually. So cooling the detector and seeing what happens to the output from the breadboard pick, but equally cooling the breadboard and then seeing what's happening to the output from the, well, seeing what the data output is to the computer. And so when the breadboard was cooled and the detector was kept warm, it worked perfectly fine. But when the detector was cooled, the breadboard and the breadboard kept warm, this thermal shift was still observed, which means that the microcontroller isn't the problem for this shifting behavior. So taking a look at some of the raw data, so I've got the VN and VP measurements here. Um, you can see that in that initial 24 minutes, when it was still relatively warm, it's working fine. And then when it's cold, it's got this sort of these linear regions here. And essentially, what's happening is the valley should be dropping. You should take the measurement, and then it should recover. But what was actually happening is it was dropping and not recovering by the time the next event came along, um, which means then that the pulse height measurements are wrong, and it's just not giving you useful information. And that is obviously a huge problem because putting on a weather balloon to look at ionizing radiation in the atmosphere, it's 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 going to be very cold. And so what I did was I implemented, I call it the valley reset, where essentially after an event, I want to force the voltage back up um, such that it can drop in time for the next event. And that modification required some changes to the microcontroller firmware and addition of some electrical components to the board. And once I'd done that, it was really a case of testing the modification. And so to do this, I developed a thermal testing procedure with a Python script to save my data. And the idea was to cool the detector in this thermal chamber and leave it for 15 minutes to acclimatize and then collect data for 45 minutes once it was at temperature. And this was achieved with a liquid nitrogen as the cooling agent. And here you can see a picture of the board in the thermal chamber. Um, and then on the right, this is just a screen showing that the current temperature was at minus 48 when I was running this test, and the target temperature was minus 50 C. So essentially, those temperatures which were expected on the balloon flight. And here is one of the pulse height spectrums at minus 40, and you can see it's pretty much the same sort of shape and distribution as that first data set which I had shown you. So that extreme shift in the pulse height is no longer there, which means that the valley reset is working as expected. Um, and thus the instrument is more ready for the low temperature environment that it would uh, be operating in. And for completeness, just to show you, I've got a sample data set in the lab when it was warm, and then you can see going from 0 to -5 to -10, all the way down to -60. There are minimal changes in the distribution with temperature, which is really, really positive. And so the next step would be that radio sonde integration, which I'd mentioned. So data retrieval. This is going to be done with a Vaisala RS41 radio sonde, and that's got all sorts of sensors on it: temperature, humidity, altitude, GPS, and that communicates with a MW41 sounding system, and you can see a picture of it here. And then the Pandora is going to be the device that speaks to the radio sonde. But for the actual balloon launch, I need to integrate the detector with the Pandora. Um, and to do that, I had to introduce a secondary microcontroller called the data pick. Um, and that's mainly to reduce the volume of data, because with that radio sonde, you can only send data at a specific rate. And if you were to send the raw data from the detector, you would end up not being able to do that. And so the data pick, what it will do is essentially it will take the raw data from the main microcontroller, package it up into some energy channels, and then pass it on to the Pandora, which will then pass it on to the radio sonde. And then in terms of the communication protocols, this was just achieved with serial, and then this was a legacy I2C protocol. And so for the actual payload, uh, it's a sort of sandwich of three different instruments. So at the top, we've got the detector I was working on, the Pandora, and then the Geiger sonde, which is a Geiger counter composed of two Geiger tubes there. And both of these instruments feed their data into the Pandora, and then the Pandora feeds that over to the radio sonde. So just to illustrate the energy channels and the packaging of data, here's another pulse height spectrum at the native detector resolution of 1 ADC. From the prototype flight, there were a set number of channels available, and this is what that data looks like packaged into those previous channels. And then these are the newer energy channels, which I'd designed as part of the current integration. And essentially, you can see that there are more energy bins, which I've made at the lower side of the spectrum. And that's based off of some low energy X-rays which were detected previously. But in terms of the major improvements, there are more channels, and you've got a greater resolution for storing these events, and also customizable bins. So in the previous configuration, there were 10 channels where you had quite a large bin width as your smallest bin, compared to the newer one where you have 17 channels and you have a much greater resolution of this of the smallest bin. And so now that I've sort of set up these energy channels, and I'm happy that they are going to be useful and give me some good data, I want to make sure that it's all working. So I'd tested this payload assembly with a radioactive source, cesium-137, and that's going to give me a high count rate environment, very similar to the count rate from the commercial flight. And essentially, in this first plot, you can see that the Pandora output, so the data that's been sent from the main microcontroller to the data pig to the Pandora and then to a computer, matches pretty well with the raw data from the actual instrument, and it's received over 99% of the counts, which is good. So it means there's minimal losses, even in a high count rate environment. And then on the right here, I've got the count rate from the Pandora, from the detector through the Pandora, as well as the count rate from the Geiger counter tubes. And that's all working there. And then for another step of verification, testing it when it gets cold again. So similar setup, and here it received almost 100% of the counts. But obviously it was a much lower, just a background count rate. So just to summarize this little section, on the temperature side, I saw that there was a shift in counts with low temperatures, implemented a value reset, and demonstrated that it was working okay. Needed to integrate the detector with the radio sonde system to retrieve data, and did that with a secondary microcontroller and basically increase the capability of the instrument. and then verified that it was all working and that I wasn't losing much data. So high altitude balloon deployment. So I was planning to do a launch, um, but it was really important that I would be able to recover this detector after the launch. And so I used a tool called the Cambridge University Spaceflight Landing Predictor. And essentially you can punch in, certain parameters around your payload. So what your ascent rate is, what your target burst height is, where you're launching from, and it will give you um, possible trajectories and end positions uh, for those parameters. And so here, if I had launched my balloon from Reading on the 1st of July, it would have landed just between Brighton and Portsmouth. If I did it on the 2nd or the 3rd, it's going in the sea. And then some of these other days, they're a bit close to the sea as well. And kind of wanted to avoid anything that was too close to London as well. And then for the 9th of July, this was the trajectory. So launching from Reading, the burst point would be just north of Milton Keynes, and then it was expected to land near Corby, but in Rothwell, just there. So came around to launch day. This was done from the University of Reading. Uh, in this black box here, it's got that sandwich of the three instruments, the detector, the Geiger, and the Pandora. And you can see there's a ribbon cable connecting the two. There's lots of tape and cable ties essentially trying to hold it all together. Um, and then I've got a picture of some colleagues from Reading. This was a 1,200 gram latex balloon filled with some helium. Um, and so for you'll see it in this video in a second. But what happened was we had the balloon at the top, and then about I think 40 meters or so of twine, the payload, and then about 4 meters below that we had a secondary tracker. So this tracker is actually this little polystyrene egg here, was provided by a colleague, Dave Ackerman. Because that would allow us to find the payload once it actually landed. And then up on the right here, this is the actual path that Dave's tracker had taken. And so you can see it matches that prediction very well. And so it was launched in the middle of the afternoon, but I'll let this play and hopefully you'll be able to see it. Yeah, so there's the parachute, which is the orange there. The unwinder wasn't meant to do that, which is why it ends up being quite a big distance between the balloon and the payload. And then these two had to be let go sort of sequentially because there's a fence around the observatory and we didn't want it to get caught. And yeah, away it goes. Yeah. So and that flight got to a maximum height of 32 kilometers. So in terms of data that I got back, uh, on the top here you can see the pulse height spectrum with those bins, but I also included some diagnostic counts which allowed me to make sure that the instrument was working properly. Um, and also you can see that the distribution of counts, at least in the channel counts, is very different from the surface, which is good because it means that there were different and higher energies detected than at the surface. Um, And then the bottom has got the count rate plot, and you can see that the maximum count rate was 236 counts per minute, which is again higher than even on the on the passenger flight, which is to be expected because at 30, or I think this was actually like something like 20 kilometers, you're very much in that cosmic ray layer. Um, And then in the count rate plot, I've also marked the burst point of the balloon. So all of these counts where it looks like it's going up again, that's just as the balloon is traveling downwards. It's encountering the same environment as it did on its ascent. And up here, I've just now put the count rate from the Geiger tubes from first one, and then the first and the second one together, and you can see that um, they 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 agree quite well. And then this is the count rate from the coincidence counter on the Geigers. And the coincidence counter will only activate when an event is detected in both tubes at the same time. And that's only going to happen really from highly energetic particles traveling on the correct path through both tubes. You can see that that only really starts about an hour into the flight, as you're again in that cosmic ray layer. Um, and so uh, this is some of the on the left is some of the sensor data from the radio sonde. So you've got the temperature profile. This flight wasn't as cold as the previous one. I think for the duration of the flight, it was at around minus 50, whereas the other one had gone a bit colder. Um, this is just the humidity plot, and it's yeah, there's not too much interesting to say on that. And then the pressure profile is pretty much exactly what you'd expect. On the right here, I've got a uh, sort of spatial map because you've got the GPS position as it was moving up. So you can see that it really hits those highest count rates at around 20 kilometers as well. But what you can do with the data, sorry, yeah, so nothing abnormal was going on there. But what you can do with the count rate data is you can actually group it by altitude. Um, and so from those early ionization profiles which I'd shown you, they would just give you a overall idea of the ionization. So you're getting this many counts. But what you can see here is as a function of altitude where those counts are coming from. And so you can actually say, oh yeah, you know, the highest counts are at 20 um, 20 kilometers and uh, it's between 1 and 2 MeV. Um, and this isn't really something that has been seen before in this amount of detail. And another way that you can view that same data is you can have a look at the count rate for each different energy bin. Um, and so lots of them look similar to the total ionization profile, but there are a few which are really interesting. So you've got the Geiger coincidence counts down here. I've not put it on yet. But essentially, these like three highest energy channels from the detector, they don't really start to become populated with counts until you get into the above the troposphere, and that's going to be because of the deposition of high energy particles depositing energy into the detector as it's in the stratosphere. and that's contrasted quite a lot by some of these lower energy profiles. um, Unfortunately, there was nothing really exciting going on space weather-wise. So I know it was in the middle of the afternoon, but there were no aurora that evening, for example. So it was relatively quiet. But that does mean that it'll be useful as a baseline for future balloon flights. Um, and then another way that you can look at the data is you can split up the energy spectra by altitude. Um, and what you can see is that as you're increasing in altitude, the distribution of counts changes. And so comparing the extremes of 2 kilometers to 33 kilometers, you can see that there is a greater abundance of higher energy counts. Um, but you can also see as you're going up through the various altitudes that the total number of counts is changing. So in that at 2 kilometers there were only 139. At 20 there's 790, and then it does dip again as you're sort of approaching that mesosphere point of the charged particle concentration. Um, so it overall, the balloon was a hugely successful flight, but that doesn't mean it was perfect. Um, for example, there was a large amount of redundant data which was produced, essentially because of some of the code which I'd written. Um, it was spitting out the same lots of information multiple times, and so there was just a lot of stuff that had to be kind of cleaned out after the fact. And I'm pretty much certain that's what caused the sounding software to crash whilst the balloon was on the descent. So the whilst the balloon burst at 32 kilometers, the final reading happened at 10 kilometers when the detector was above Northampton, but the balloon didn't actually land until didn't yeah, it landed in Rothwell. So there's 10 kilometers of descent data that's missing, but that's not so important because the descent doesn't allow you to get that same kind of pace data collection um, as you can on the ascent. And here are a couple of pictures. When Dave found the detector, it was in a field just off of, I think, a dual carriageway, um, and he kind of had to wrestle uh, through this field to untangle all the twine, and yeah, there's a picture of his tracker there. Thank you for your attention. Have you got any questions?
Right. You can either pop your questions into the chat, or just unmute yourself and shout out. I'm going to have Joe's prerogative and ask the first question. All the reactions and the particles you're detecting during this flight, are they creating things that stay in the atmosphere? Are they actually producing radioactive isotopes of atmospheric atoms or molecules?
Um, so I'll just one of the earlier slides on to have as a. Oh,
You've unshared
yeah.
yourself, I think, when you close the screen.
Um, yeah. So one thing that can happen with these cosmic ray primaries is they can interact with things like nitrogen in the atmosphere and cause them to become excited. And then it's through some of those de-excitations that you can have the emission of gamma rays, which is one thing that this detector would be picking up. And so, uh, in that sense, you do have something that's, you know, becoming. I don't know if radioactive is the best word, but it's becoming ionizing, um, and that energy does go somewhere. So yeah, it's I wouldn't necessarily say that it's keeping radioactive nuclei just kind of floating around in the atmosphere, because if it's charged, something else is going to hit into it. Yeah.
Yeah, because the obvious thing that was crossing my mind was sort of something like carbon-14, which does float around in the atmosphere and must come from somewhere. And I wonder whether that was one of the things that can create it. I have a question in the chat. It's about the balloon launch
Yeah.
and the actual process and permissions of getting a balloon into the air. Can you just sort of buy one on eBay and launch it?
Um, so there is something like that because I think that's almost what Dave Ackerman does. But I think you probably still do need a license for it. One of the reasons that we did it with the colleagues at Reading is because they have a license and permission to launch balloons essentially, uh, I say whenever they want, but between I think 9 and 5, Monday to Friday, um, is when they've got the permission to do that.
Okay, we have two more questions. One from the chat and then one from Paul. Um, did you consider using a heater to control the temperature of the detector so you didn't have to go through the processing or and correction of the values?
Yeah. So you could use a heater, but then you're essentially increasing the total amount of mass and the power considerations. Um, and when you're like it, at that point, it's quite difficult to make sure that the balloon actually gets up to the altitudes that you'd want to see these high energy interactions. Um, and so that's the main reason why a heater wasn't used. One thing that we did investigate was using um, a sufficiently a sufficiently insulating thermal shroud, which instead of having just like the 3D printed box on the outside, it would actually be made of a more insulating material, and that was a project completed by a colleague, and we found that essentially it keeps it warmer for longer, but it will still get cold.
Okay, Mr. Hearn.
Yeah, thank you. Loved the description of the development of the instrumentation, Justin. That was great. I have a question about the calibration. At the beginning of your talk, were you showed some charts that gave the ADC counts, millivolts against ADC counts against the energy of the particle that you were measuring. How did you get the calibration from the ADC counts to the GeV of the uh, fundamental particle?
So I've got another show you here. So the relationship there between uh, ADC and energy, that's to do with the particles um, which are being detected, not necessarily the energies of the like cosmic ray primaries, for example. But the way that the calibration was performed was again using a radioactive source. This was some of the experimental apparatus where essentially the cesium source will have characteristic energies, and you can identify those energies in the spectrum, and then you can essentially do a linear calibration for it. So cesium 137 has a really large gamma photo peak at 662 keV, and then you get some additional peaks from the scattering based off of the lead surrounding. And then there are also a couple of other features in the spectrum which you can basically then uh, have sufficient data points to determine the relationship between the two.
Okay, yeah,
Mm.
a radioactive source. Yeah, thanks. That's excellent. And then just some confusion that is probably only true for me. You when you were talking about the instrumentation in the balloon, you said GM tube, and then earlier in the talk it was a solid state device you were using. Um, am I confused or did I mishear you?
So there were two two instruments in there. So
Ah, okay.
yeah,
Yes, okay. Yeah, I can see it's a sandwich with two detectors.
Yeah.
yeah.
Thank you. Yeah, thanks very much, Justin.
Um,
Any more questions, anybody? It's all gone quiet on the chat. Okay, as it's gone quiet. Well, Justin, thank you very much. I think you found that I certainly found that interesting, and it's nice to hear how an instrument is developed from scratch. For those of us who've not been in that environment, how you actually build something from scratch, get it calibrated and qualified for flight, and then get some proper data off it, which serves a useful function into the future. You know, calibrating the detect. Are you planning to fly it again?
um, so I won't be because I've got a new position starting in March, although that will still be designing detectors to put on weather balloons. But I think my supervisor, Karen Applin, uh, she's probably got some plans to launch it again. Um, but I think so lots of the changes which I'd made as part of my PhD and the research that I was doing were very kind of hacky. So there was, air wiring stuff, not using like the correct. Yeah, I think I had like some through-hole components when, really they should have been surface mounted. And so we're currently like formalizing those changes into like an updated circuit board. So it won't be as kind of slapped together. And so probably it would be after that stage that there might be some more small flights.
Yeah, okay. The anecdotally, I'll share this from a previous presentation we had of a cosmic watch detector being flown on a balloon flight. The students preparing it were so concerned with the temperature problem that they packed it up in a thermal jacket with a one of these microwaved heat packs inside rather than a battery source.
Yeah.
Flew it and it stopped working because it got too hot. Oh, we have some more questions. Um, Whereas a question about the cost of the payload,
Um,
if that's not secret.
uh, so yeah, I don't know what the exact cost is. It's currently still going through licensing at the moment. But yeah, I should have mentioned A Squared Technologies are the company I think who are going to be manufacturing these when they're ready. Um, but yeah, yes,
Okay.
I don't know entirely. I'm
Yeah.
sorry.
And a rather simpler question. What type of microcontroller ADC were used?
Uh, sorry,
Yeah, the microcontroller in your package.
yeah.
The question is about what type of microcontroller was it?
Oh,
Um,
okay.
and did you use the ADC on the microcontroller or a specific? Huh?
Yeah, yeah. So it was a PIC 16F676. So it's not the newest chip available. I think there's almost a direct upgrade off of that chip. But it had a yeah, and I was using the A to D converter from the microcontroller, and it had 1024 channels. So one thing which I've suggested that should be changed going forwards is that A to D converter uses a 5 volt as the comparison voltage, but none of the voltages in the measurement section need to have that 5 volts. So like the pulse analog will sit at about 3.2 volts, and so really you could get away with using say 3.5 as the comparison, and that will free up an additional range of ADC channels. Yeah.
Okay. Any more questions? No, I think it's gone very, very quiet. Well, Justin, thank you very much.
Thank you.
And if you do go forward designing more instruments that are of interest, you would be very welcome to come back. And if Karen Aplin has got another PhD candidate lined up for the next phase and they take it further, we'd be delighted if they'd come and tell us about it.
Yeah, I'll definitely pass on the
Yeah.
message.
So thank you very much.
Thank you.
Just one notice, I'll say it again, I said it last time. The European Amateur Radio Conference will be coming to Harwell in the first weekend of September this year. And Justin mentioned ISIS. We're right next door to the Diamonds light source. And one of Paul and I's jobs for the early part of this year is to see if anybody will let us go and have a look round. So that's potentially one of the things that we'll be able to see when we're at Harwell. It all depends on whether it's working, running up, closed, or even they just don't work on Saturdays. So we will keep you informed how we get on with that. So thank you very much, everybody. And until next month, good night.